Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving a very interesting problem. I guess I could call this homemade because I thought about this idea, and we've done similar problems, but this is going to be an interesting problem because we're going to come up with a formula which you can apply to very many situations, and I'll talk about that hopefully towards the end. We're also going to look at the results from Wolfram Alpha. I know I always mention it because anytime I make a video, I also want to check what Wolfram Alpha has to offer, and sometimes it just falls short. But anyways, that's okay. No offense. aplusbi and c+di are given complex numbers, and as I said earlier, we're going to come up with a formula. Okay, since I'm kind of lazy, I didn't want to write down the final answer, so it's been typed up and I'll show you. Hopefully that is gonna look obviously nicer because my handwriting is kind of awful, but anyways. So we have this z, which is what we're trying to solve for. Z is raised to the power a plus bi, and it's equal to c plus di. So a plus bi and c plus di are given complex numbers, and for example, if we are given a situation like this, you can pretty much apply the formula to this. Like c is going to be 0, d is going to be 1, a and b are both going to be 1, and then we'll get this particular problem. But we're going to solve this in the general sense, which is what makes this problem is pretty interesting. So if I made a playlist of interesting problems, I think this problem would definitely qualify. What do you think? Let me know. Maybe we can make an extra playlist, because I made the basic, medium, and I think hard problems. I don't think I have a lot of hard problems, but I also have a lecture problem series. By the way, if you're new to complex numbers, go ahead and check them out. I also made a post at Cybermath, which is my other channel, my first channel, and this is aplusbi. What's the name of this channel, right? And we use it all the time. Okay, anyways, so let's go ahead and take a look at the complex exponentiation first. Z to the power w can be written as e to the power w ln z. Ln of a complex number is also a complex number, but ln z is multi-valued. There are basically infinitely many ways you can write it because of the argument. If you use the principal argument, you're going to get the principal value. Otherwise, you can just keep adding 2 pi to the argument or the angle. Anyways, we're going to talk about some angles here, moduli, and also a little bit of trigonometry. Why did I say I made a post? Because that post is actually concerned with the stuff that we're going to use. I'll tell you when we get there. So let's go ahead and apply it to z to the power a plus bi. Remember, we're solving for z. Always keep that in mind. So z to the power a plus bi from here is going to be e to the power a plus bi times ln z, right? Okay, a plus bi, and then that'll be multiplied by ln z. Now, what about the right hand side? Okay, we'll get to that next. So we want to write, we were able to write z to the power a plus pi in exponential form. Let's go ahead and do the same thing with c plus di. How do you write a complex number in polar form? Easy. R e to the I theta. What's theta? R is the modulus, which is the absolute value, or some people call it the norm, and theta is the argument, but there are infinitely many values. If you wanted to consider the principal value, then you just take the smallest angle between negative pi and pi, right? And that becomes your principal argument. The absolute value, or R, is basically just the distance from 0, so it's going to be given by the square root of c squared plus d squared. And tangent theta, if this is your complex number, and theta is the argument, then tangent theta can be found from d over c, because cosine is c over r, sine is d over r, and you guys just divide them. Make sense? So from here, we get 3 different results. Theta can be arc tangent of d over c. So if you arctan both sides, but this is what the post is about. That's not the only value. There might be other values. For example, depending on the values of c and d, you might be in a different quadrant, right? Okay, if you're in the 3rd quadrant, tangent is still positive, but you kind of have to add pi, because that needs to put you, that gives you an acute angle. You have to add pi to get the actual angle. Make sense? Anyways, go ahead and check it out, and you'll see what I'm talking about. Check the post on CyberMath. Okay, let's just go for simplicity's sake with the first one. Let's just assume that C and D are both positive. I mean, without loss of generality. Remember that expression you see in proof books? Okay, cool. Now let's go ahead and put these two together. So now we have R times e to the I theta. So c plus di now can be written as the square root of c squared plus d squared, which is r, times e to the power I times theta, which is arc tangent d over c. Okay, we're going to come up with the formula. So when we find z at the end, it's just going to be in terms of a, b, c, d. I'd like to say it's as easy as a, b, c, d, but that's not the case. You're going to see what I'm talking about, okay? So now let's go ahead and put these two together. Remember, on the left we have z to the power z to the power a plus bi, which was written as e to the power a plus bi multiplied by ln z. And now on the right, we have the square root of c squared plus d squared times e to the power I times arc tangent d over c. Okay, I could probably just replace this with that, but anyways. Cool. Now we have this interesting expression, and we're gonna natural log both sides, which is gonna bring down the exponents for e, and then this expression will be ln, or natural logged, and of course that's going to be a real valued ln, because we know that this is non-negative. And obviously I don't want it to be 0, because that would be meaningless, right? You want definitely, I didn't say that, but you probably guessed, c plus di does not equal 0, okay? Which means c and d are not 0 at the same time. So let's go ahead and natural log both sides, and we're going to be getting something like this: a plus bi multiplied by ln z equals ln of this expression, ln of square root of c squared plus d squared plus I times arctangent d over c. Again, I did some simplifications to avoid some complications, but if you wanted to write a more general form, that's perfectly fine too, because this is already complicated enough. And then the next step would probably be dividing both sides by a plus bi. And you could also do one more thing here. You could write this as c squared plus d squared to the power 1/2 and bring the 1/2 to the front. So let's go ahead and do that. Get rid of the radical, because it looks better this way. And then I'm going to go ahead and do 2 steps at a time. I hope you don't mind. Divide both sides by a plus bi. And guess what? That's going to give us ln z. Now here's what you need to do next. I mean, you don't have to, but I did it. And I basically multiply the top and the bottom by the conjugate of a plus bi, which is a minus bi. So ln z became 1/2 ln c squared plus d squared plus I multiplied by arctan d over c. And then this whole thing was multiplied by, and I could probably just use a different color maybe. Okay, multiplied by a minus bi. And at the bottom, I also have a minus bi times a plus bi. By the way, that just turns into a squared plus b squared. Makes sense? When you multiply this by its conjugate, it's going to turn into sum of 2 squares, which is also the absolute value, or modulus squared. Makes sense? So far, so good? Do you have the patience so far? Now, we're going to have to distribute this and kind of arrange the terms, real and imaginary, separately. And then to find z, we need to do e to the power ln z. Okay? Let me go ahead and show you what the results are, and then I'll show you the result from Wolfram Alpha. Okay? Make a guess. Do you think Wolfram Alpha was able to find what I found? And ta-da! Drum roll! This is what I found. Don't you love it? It's beautiful. So z can be written as follows. Now you can think about this problem as follows. Like, let's say, replace a, b, c, d with some numbers. Of course, they have to be real. And then plug them into this equation and see if you can get the right answer. Are you ready to check what Wolfram Alpha has to offer? Okay, let's go ahead and check it out. Ta-da! Wolfram Alpha can only give us this expression, which is kind of weird, but what can you do, right? Shortcomings of AI at this point. Anyways, this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.